we were looking at examples of irreducibles and primes and whatnot. So, uh, um, actually, let's do this. So what I mean by this notation up here is these are polynomials with complex coefficients with one caveat, and that is a constant term has to be real. All right, so this is all stuff that looks like R0 plus x f of x, where f of x that arbitrary polynomial Cx. Notice that this is a subring of this, right? In this ring, the element x is an irreducible, but it's not prime. So you can argue that it's an irreducible just by that looking at the degree of it. If x breaks down, then the degree of x is 1, so one of the two, so it has to break down into degree 0 times a degree 1. But in this ring, notice that everything's at degree 0 is a unit, right? Because degree 0 means it's a non-zero constant. Notice here, oh, and it's not prime because in this ring right here, notice that you love the obvious, don't you? X divides that product, but it doesn't divide the individual I, right? However, here, X is irreducible, not prime.
Why doesn't X divide I? Oh, never mind.
There is no I. That's right. There is no spoon. Here's an example designed just to piss off graduate students. What about here? What's the status of X here? Irreducible, prime, something else.
Not prime for the same reason that you have there. So we could have X and I X.
Right, right. I mean, certainly it can't be prime exactly because of this example up here. But here, X can't be factored into irreducibles at all. Does that anger up the blood a little bit, right? I mean,
is X the only thing in there that can't be factored into irreducibles?
well, okay, I can cheat a little bit on you and say, well, X squared can't either, and so forth and so on, right? But in the spirit of that, sort of. Does anybody see what the problem is?
elements of Z.
What's that?
Elements of Z.
That's exactly right. Let's suppose, let me actually justify this. Suppose X is a product of these, where each of these FIs. So these FIs are just polynomials with real coefficients, I'm sorry, complex coefficients with a constant term in the integers, right? Okay, so it is kind of useful because remember, all of these factors, of course, living in R3, they certainly live in R2, right? Because all these rings are all subrings of R2. What can you say about the degrees of these FIs?
They have to be a one.
Well,
Bigger than one.
exactly one of them has to have degree one, right? So notice that. And of course, so I'm assuming that I can factor this into irreducibles. So these are irreducibles, whatever that means, right? And that's where the problem's going to be. Without loss of generality, F2x, F3x, all the way up to F3x, all have degree 0. So that is to say, Fi x is in the integers for all I between 2 and k. Somebody tell me what then. So in particular, what this means is this product is just some integer, call it capital again. And of course, it's non-zero because otherwise you got problems, right? So now what do we know? Well, what does F1x look like? Has to. Agree? What's the problem with it?
If you can divide that as a unit.
This is actually not irreducible, right? Because notice that F1x, which is x over n, I am such a big fat cheater, is 2. And notice neither one of these factors is a unit, right? And really, what I'm really such a cheater here. I couldn't do that in these other two examples because your coefficients came from the field. So anytime you pull something out of the x, you're pulling out a unit. With the z here, I'm pulling out stuff that are not units. So this thing right here is not irreducible. And there's your copy. So in fact, the status of x here, it goes from prime to irreducible to, I can't even factor this into irreducibles. All right. Kind of strange. Okay, so here's my question here. And this might be considered as inspired by your question as well, because you said, is X the only thing that can't be factored into irreducibles here? And the answer is no, but spiritually, sort of. Right? So the question is, when you think of an example of an integral domain where there aren't any irreducibles at all. Yeah,
The set of all roots of monic integer polynomials.
that's one of the best examples that you can get here. I'll give you a couple of examples that are. Show that's a little bit different example. And actually, the problem with this example here that I'm gonna get you is that it's not clear it is a ring, but we're gonna actually learn that it is. Let's let Z bar, I'm gonna define the set to be the set of complex numbers such that P of Z is equal to 0 for some, and this adjective is very important. Well, let me recall a polynomial f of x in some ring, or some polynomial ring, is monic if its leading, that is highest degree, coefficient is 1. Now, here's the flaky part of this. This is the ring of every complex number that is the root of some monic polynomial. So in particular, any integer is in there because an integer is a root of x minus whatever the integer is. But you also get to throw in every root of a monic quadratic. So in this set, I have the square root of 2, I've got every quadratic. But then I've also got like the 5 complex roots of like x to the 5 plus 2x plus 6 and everything like that. Now, it's not really clear that this is a ring, is it? Right? Because if I walk up to you and I give you, I don't know, I, and then I also say, well, I'm also going to give you one of the complex roots of x to the 5th plus 2x plus 6. Now add I to that. Is it clear that there's a monic polynomial that that's the root of? And the answer is actually yes. And we're going to prove that later in the course. Is it clear that the product of those two is the root of monic polynomial? We're going to prove that this is all true. By the way, if I give you the polynomial for one and for the other, good luck finding the polynomial. It's complicated. It's very complicated. I can give you a bound on what the degree's got to be, but finding it in general is difficult. But if you hear me now and believe me later that this is in fact a ring, then there are no irreducibles here. Now that Z bar is a ring, in fact, it's an integral domain. This is a subring of complex numbers. And can anybody explain to me why this doesn't have any irreducibles here?
It's kind of like the idea if you take 2, you can write 2 as the square root of 2 times the square root of 2.
Okay.
And then you can keep doing that forever.
Right.
So if you take anything, the square root of that's going to be.
So let me go about it this way. So let me sketch Z bar as no irreducibles. Suppose alpha in Z bar is irreducible. Oh, and I guess there's let me convince you also, if I want to be super careful, I guess I should probably convince you that Z bar is not a field. Because otherwise it would be kind of stupid, right? I'll come right out of the barrel and tell you that. Well, by the way, can anybody name something that's a complex number that can't possibly be in Z bar?
Yeah.
Okay, so you could throw transcendentals at me. Let me ask you this, can you think of an algebraic number? 1/2, right? Is it clear that 1/2 can't possibly be in here?
Because of the mind.
What's that?
Because of the mind.
Right, I'm gonna sketch that really quick too, because I think it shows you why, it's the beginning of why monic is important here. Suppose 1/2 is in Z bar. Well, what that means is 1/2 has to be a root. X to the n plus m sub n minus 1, x to the n minus 1 plus m sub 1 x plus m naught, where the mi's are integers. Everybody okay with it? Okay, anybody know how we get a contradiction from this?
2x minus 1, have to divide that.
Oh, something like that. So what this means is 1/2 the n is
Can we say the degree must be no more than one, because in Q of it, when, you know, like you can.
it turns out that's true, but it
Can do something like this, is the much things argue like irreducibility.
yeah, you probably something out in Gauss's one, that's right. So this actually brings to a question that's going to ask later, like, for example, if you take integral equations, right? Just because it's algebraic, how do you know it's not integral for some larger degree, right? That's an interesting question. But what I've got written here is, well, you know, being a child of cousins, I don't really like fractions that much. So I want to kind of clear this out a little bit. I'm multiplying both sides by 2 to the n, right? Now, maybe the contradiction is more obvious, right? That's even, that's odd, right? And basically, this kind of hinges on unique factorization, the fact that the integers has unique factorization. So this actually can't be a field, because in this big ring, if you believe that it's a ring, in this big ring, 2 is a non-unit, right? And we'll learn some stuff that takes care of that as well. Let's suppose that alpha is an irreducible. Well, since alpha lives in here, one thing I know is that alpha is the root of uh, well, no, alpha's the root of that thing. Well, note that note that if you look at the polynomial p of x squared, which is x to the 2n plus m's min minus one, x to the two min minus two. M1 x squared plus M0. All of its complex roots are in there. And so essentially notice that notice that the square root of alpha is root of this. Hence, and this is enough to leverage a contradiction of irreducibility. Notice that if either one of those alphas is, if either one of those alphas is, right, if either one of those alphas is 1/2 is a unit, then alpha is a unit, right, which would be a contradiction. So what we've shown here is every non-unit has a square root, so there are no irreducibles. Kind of hard to factor there. Here is one that has a you can also build these things by just kind of stair stepping and just creating new sets of divisors every time. That's a big construction. Here's another interesting construction. Um, I'm going to go over this more carefully. This is kind of a look ahead to localizations. Consider okay, so what do I mean by this? This is the group ring F over positive reals. What I'm doing here is I'm basically generalizing polynomials, right? Except now what I'm going to do is a typical element in here looks like alpha 0 plus alpha 1 x. Well, let's say lambda 0. Where the lambda i's are in the field and alpha 1 less than alpha 2 less than alpha k are all in the positive roots. So basically, this is just like polynomials over a field, except now I'm being very liberal about what I'll let you use for exponents. You don't just have, you don't have to restrict yourself to positive integers for exponents. You can use any positive real number, right? Have all kinds of crazy crap. X to the x to the pi power plus x to the fifth, whatever you like. Now, this is an integral domain, right? Let me talk through it. Would everybody agree that when you add two such polynomials, you still get a polynomial like that? And when you multiply, it's just like doing the degrees, you add them up and you get the sequence here. Now, what I want to do is I want to notice this is basically the set of all of these polynomials where lambda 0 is 0, right? So it's generated by every positive power of x. basically, here's another sloppy way you can think about it. These are all the polynomials, if you will, that when you plug in x equals 0, you get 0, right? This is a maximal ideal because when you mod out by it, you get the field F that we started with. Agreed? Its complement I should have called this something. I'll call it R. This is the set of all f of x in R such that f of 0 is not 0. So it's everything where the constant term is not 0. Notice that this forms a multiplicatively closed set, right? Because whenever you multiply two of these polynomials, if they both have a non-zero constant term, the product's going to have a non-zero constant term still. Everybody okay with that? And probably as you've seen building up to this class, what can you do with a multiplicatively closed set? You can let all those little things be denominators, right? And so I'm going to let R localize it in. I know this notation sucks, right? R localized at S means numerator from R, denominator from S. When you see the notation with an ideal instead of a multiplicatively closed set, that means the denominators are everything that's not in M. Right? These things are synonymous here. They're the set of f of x over s of x, where f of x is anything in R and s of x is s. So this is just the collection of stuff that has a non-zero constant term. Okay. So for example, I'm going to ignore, because basically what you've done is you've taken all the polynomials that have a non-zero constant term and turned them into units, right? So from a factorization point of view, you can forget about them. So for example, if I have something like where alpha 1, alpha 2, alpha k are reals and positive, notice that I can pull an x to the alpha 1 out of this. Right? Everybody agree with that? And now, from a factorization point of view, I can effectively ignore this. Right, this original thing is just x alpha times a unit. X alpha 1 times a unit. Everybody agree with that? So basically, in RS, you have three types of holes. Zero. There's one of them. Two. A unit. That's another type of element you have. And everything else that's not a unit looks like this. So everything in this ring that's not zero and not a unit basically is x to the alpha power times something. Now, somebody tell me why this has no irreducibles.
Smaller alpha.
That's right. There's always a smaller alpha. So if you ignore zero and you ignore units, if you have a type 3 element, which is what the non-zero non-units look like, there you go. So there's no irreducibles whatsoever. Everything is like sand, it keeps breaking down. Good Lord, I run my mouth a lot. Okay, any questions on that? Okay, so we talked a little bit about localizations and stuff. Now we're going to build on this. I'm going to do a little bit more than this in the notes. Multiplicatively close. Sets. Multiplicatively closed sets, I think, are very well named. It's very suggestive terminology. What does it mean to be a multiplicatively closed set? Well, it's a set, and if you take two elements in it and you multiply them together, it's still in there, right? If you add them, who knows? But if you multiply them, they're still in there. This is, for those of you that have seen this sort of thing, this is paired up with localizations quite a bit, because localizations you can think of as sort of fractions. And the way you add fractions is you multiply the denominators. And the way you multiply fractions is you multiply the denominators. So the setup behind one philosophical approach to why you consider multiplicatively closed sets is because those are exactly the sets that you need to form denominators, right? So let's just define these things first. Let R be a tone. Oh, I'm not going to let a domain definition. Let R be one. A subset. I don't want it to be the empty set. R is multiplicatively closed if S and T and S imply ST is correct. So multiplicatively closed is just what you think. Two, a subset. I don't want it to be empty, and R is saturated. This is kind of the dual motion, if you will. If ST is an S implies S is an S. So in other words, it's a saturated set if it contains all its divisors, right? So saturated, if you have a product of two things in the ring that knocks you into the set, then every factor of that has to be in there. So in particular, if you have a commutative ring with one, every saturated set must contain
one.
Every saturated set must contain one for sure. And in fact, more generally, it needs to contain all the units. Yes.
For saturated, are you missing the T, or T must be in this?
It's symmetric. So basically, an arbitrary divisor has to be in there. So yes, T has to be in S as well.
Oh, both of them have to be.
That's correct.
Okay.
Let me make some notes. Notes on the definition, if you will. Usually, is an additional modifier for multiplicative set. What I mean by that is a lot of authors don't even talk about saturated sets unless you're already talking about a multiplicably closed set in the first place. However, there's no real reason to do this, right? You saturated, it can be saturated in a bubble. In fact, if you look at the set complement of an ideal, right? One are an ideal proper so that the complement is not this set, the complement of an ideal in a ring is always saturated. Let me prove that for you. Suppose A, B is in S, where A, B are elements are. And suppose that A is not an S. What does it mean for A to not live in S? It means that A does live in I, right? Which implies AB is in I, because I is an ideal, and this is the contradiction. Right, because we assume that AB is not an I, right? So the complement of an ideal is always a saturated set. It's almost never multiplicably closed. In fact, if I take an ideal and its complement is, well, its complement, take an ideal, its complements are always saturated. Anybody know necessary sufficient conditions on an ideal for its complement to be multiplicably closed?
Maximal,
What's that?
is it maximal?
That's too good.
Prime.
Prime. That's right. That's exactly right. Okay. Let me make one more note. 2, usually S is assumed do not contain 0. On the surface of it, there's no reason why you would think you would have to make this assumption. You don't, but I'll show you when we start talking about localizations. What happens if your multiplicatively closed set contains 0, then everything's correct, but it just turns into uselessness. So, oftentimes you will see that written, let S be a multiplicatively closed set that contains 0, et cetera, et cetera. There are all kinds of multiplicatively closed sets. Let R be a commutative ring of 1. Here's some multiple sets. U of R, this notation means the units of R, is multiplicatively closed and saturated. So the product of 2 units is a unit, no problem there. And if 2 things multiply together to give you a unit, both of those pieces have to be units. So the units are multiplicatively closed and saturated. We've seen the complement of an ideal is always saturated. 2, if P is prime, P complement R minus P is multiplicatively closed and saturated. if R is a domain, well, let's start there. Let's let S equal R minus the zero element. This is saturated and multiplicatively closed if and only if, condition on R. An interval domain. Let me give you something else. Here's a bigger example. We'll get to an theorem about this. Suppose I have a collection of non-empty. Suppose I have a collection of prime ideals of some ring R. Then if you take the union of that collection of prime ideals, just throw it all in a big basket and look at the complement of that union, is that S is multiplicatively closed and saturated. And in fact, here's the rub on this example. I need no more examples because that's a theorem. In fact, that characterizes multiplicatively closed saturated sets. A multiplicatively closed set, the community ring of identity, it's multiplicatively closed and saturated if and only if it is the complement of a union of prime ideals. Notice every one of these has this in common. The units, what's my set of prime ideals? All of them, right? The units are the complement of the union of all the prime ideals, because the units don't live in any proper ideal. This is where lambda had one element in it. This is the single prime complement. And this is the differentiation here is, if you recall, one of the things we had is zero is a prime ideal in the commutative ring if and only if R is a integral domain. So it's all coming together. Okay, any questions on that? Mm-hmm.
Can you say anything just off the cuff, about R minus all the, like, if you remove all the nilpotents?
If you remove the nilpotents.
Yeah.
So what you're doing is you're removing now the intersection of all the primes. And so what do you do? You're gonna take R and remove all the nilpotents. So what you're doing is you're taking out everything that's in every prime. That won't be a multiplicatively closed set in general, because you might have zero divisors that aren't nilpotent. Right, like for example, in Z6, throwing out all the nilpotents just means throwing out zero.
Right.
And now it's not multiplicably closed because you have 2 times 3 is 0, right, which is no longer in there. Right. Here is a very interesting theorem. This is 1.4 point something 2. What are the bring one and I and R and I. And just for giggles, I'm gonna make this a proper ideal. If are such that S intersect I is empty. Okay, so let me point out a couple things as I develop this theorem here. Here we have a large elliptical ring, and we have an ideal that's proper. Right? Now, somehow we're able to find a multiplicative set S such that there's no overlap here. Right? Let me point out that this, of course, means that the set S doesn't contain zero, right? Because if S contains zero in this particular case, then it would overlap the ideal for sure, right? Then there exists a prime ideal. P containing I such that P intersect S is empty. And P is maximal with respect to this property. So what this means is, if I have any ideal that misses some multiplicative set, I can sprinkle some fertilizer on I and grow it to a prime ideal P that contains it and still misses S. This is actually a very powerful theorem. I lives inside some larger P that also has the property that it misses S. This tool we will be able to use to leverage a lot of things later. What I mean by the fact that P is maximal with respect to this property is that if you have any proper ideal that contains P, so if you make P, if you put some more dog poop on it and make it grow a little bit bigger, then it will actually overlap S, right? So P is as big as possible without hitting S. Let me point out that P is may not be unique. There might be other maximal P's. There might be a whole family of them that are maximal with respect to that property. Okay. I think that's probably, we're going to talk about why this is true next time. And this is probably a good place to put it for now. Any questions? All right. Well, I will see you folks on